Yeah. It's not smoky today. It's an out-of-sight day, but it's still cool. Anyway. Wow. Draw the structure of the following polyatomic ions. So these things have charges, and we know that ions have charges because you've gained or lost electrons. So when I see ammonium, NH4, that positive, the only way to get a positive charge is removing a negative electron. You're at 0 and you subtract -1. That's what happens. And I have, for example, cyanide, but it shows you nitrate or NO3 minus 1 or whatever. If you have a -1, that means you have one extra electron. If you add a negative, you have a -1 charge. So first thing you got to do is look at your ions charge. You have one extra or you have one less. If it was 2 minus, you'd have 2 extra. Okay, so now switch in there. Ammonia. So what I'm thinking is that we have N. I'll draw N. And normally, nitrogen go with 15 columns of 5 valence electrons. I'm not going to draw it first as NH4. I'm going to draw the individual. So I've got 1. I'm doing this on purpose here. 2. So it isn't attached. We're going to lose something. 3. 4. 5. There's a nitrogen. You've got 4 hydrogens. I'm not going to draw 4 hydrogens. Single electron. Hydrogen only wants to bond once because it wants to be like its row, 2 electrons here. The other ones, everything else you're going to assume, that's entirely different, that you want 8 valence electrons. There's an exception that we'll talk about later. And there's other exceptions, but we won't get into it. Okay. Now, with this, I tried hitching this thing up. Well, you know what? I said I wasn't going to do this. I'm going to draw all 4. Separate. Now let's think this through. I've got nitrogen normally. And you see there's no way to get 4 items attached to it, right? There's only space for 3. 1, 2, 3. And that would be maybe this one, and this one. Attached. Okay. I've got to get a 4th one on there. But then I remember. That means I'm missing an electron. Just thinking this through, which electron from my Lewis diagram of nitrogen would I remove? Top, bottom, left, right. One of the top 2. Yeah, it's arbitrary. So I'm going to just put it up here by the arrow. Just obviously you can't do that anymore. You can just maybe put a circle in the line. Now I can bond 4 directions, right? But I have a positive charge. I'm going to just put a plus in. It's going to be like plus because I've removed an electron. That's what I'm pitching on. Does that make sense? Do that. Well, let's draw the diagram. I know there's going to be a charge, so I need a big fat square bracket. I know now that I can go 4 directions. Put a hydrogen. End the bracket, and I have to put plus sign because there's 1 fewer electron thing, 1 electron missing compared to what would be expected. Does that make sense? First polyatomic ions go, that's the only one that's positive, ammonia. You remember from your list, almost all of them are named. So ammonia, that's the only common one for us. I'll update the attendance and then we'll talk about cyanide. Okay, so cyanide, Cn minus 1, that's one extra electron. I'm going to do the same thing that we started with. I'm going to consider all of these, well, there's only two, separate. So carbon, 14th column, 4 valence electrons, and they're all single. Carbon can bond 4 times, whether it's a combination of doubles, triples, or singles. Nitrogen, on the other hand, 15th column, we just did it, so I'm not going to explain it. Okay. I look at this. And I think, so 1, 2, not that I've drawn like this, but 3. I can see there's 3 matches. I'm still getting an extra, or an unpaired electron with carbon, right? That's my creed. But we're told that we have 1 extra electron. So where do you think this extra electron is going to go? Yeah, and I don't care if it's the top, the bottom, left, right. Let me show you. You'll see why I do it this way. I just put it there, it just happens. So it's arbitrary. Since I put it there, I'm going to go with carbon. And I'm going to just, you don't need to use another color, but I'm trying to show you. And then I'm going to go with triple bond nitrogen. Okay, that's good. Nitrogen still has a lone pair. I'm going to put it just for symmetry reasons here. If you put it on top of the nitrogen, make it look like German Humbach. That's fine too. But I mean, this is that actually represents more where the electrons sit, as far away from the triple bond. More about that though as you throughout this class. I can start the third chunk of lesson. Okay. I'm going to do one more on here. There's a reason. So can you guys just jot in one right here? Example, let's just say. NO2 nitrite. Here's one. It's got a little something extra. Well, it has an extra electron, but I consider this one. Well, I'm going to draw individuals. And oh no. 1, 2, 3. Oxygen twice. 16th column, so 6 valence electrons. 2 pairs, 2 singles. And I'll put this one. Okay. I know that I have an extra electron. I use blue for some reason, so I'll use the extra electron as the green. Let's try hitching this puppy up. Which one do you think is going to be the middle, the central? Yeah, because it can bond more times. It's a good hunch. Okay. I'm going to go with M. Then, each oxygen wants 2 bonds. I think it can satisfy one of them. Let's look. If you have 3 things, by the way, the best way to separate them is like that Mercedes symbol. What I'm saying is like this. Isn't that Mercedes or whatever? You know, it's like an upside down Y. You can make it like a Y, but I already drew the N with the top. I think of this, by the way, as the spot, the electrons. That's why I want the electrons on. But O, O, I'll figure out the electrons out. Okay. Now, each oxygen wants two bonds. Nitrogen can only bond 3 times, so I'm going to only attach one. That means 2 pairs. This one has 2 pairs. I'm trying to draw it in there. The first one that I drew on the left? Let's say it's this one. I bonded this and this, and then these guys are still there. Or they're still safe. That's right, we have an extra electron. But if I added another electron to the end, it would be even less bonding. So, what Kate is just saying. The last time we put an extra electron on carbon. But that's not the problem. We actually don't have enough. In the carbon case, we had 3 bonds and we still had a single single. The single isn't sitting around on the nitrogen. You see that? I started talking to you. I still have a single right here, don't I? I've only done, I'll say it's this second oxygen. I've done one of these. I still have this guy sitting here. So where's that extra electron going to go? Probably on that single. Oh. I'm going to deliver that here, and it's only colored just so that you can tell the difference. Okay, I need a square bracket. And you know what? I needed a square bracket around my other calculator. This one. Incorrect. I would not give myself full marks until I did this. Make sure you get that. Back to the NO2 nitrogen. Bracket has an extra electron, so I indicate that. Now, I'm going to squeeze something in here because it's arbitrary which oxygen had the double bond. Well, that's what I just tend to work that through. So I'm going to do something, and really it exists as, and I'm going to squeeze this one in. I know it's going to do this. Really what it is that double bond, single bond system, it flips back and forth in this thing. It's shared. So like a shared double bond. Call it a resonance. I'll just draw it and then talk about this. So it's that, which is equivalent to this. Try to squeeze all the electrons in here. 1, 2, 4, single. Then I gotta put an extra electron. Hopefully that's showing up. Then the double on this side. So what this represents, you guys see that? Some of my dots are fast. Well, it's like, it's a bit of this, it's a bit of that. It goes back and forth, back and forth. Really what it is, and I won't draw it now, but it's more like, this isn't a true double bond here, and it isn't a true double bond here. It's kind of shared between the two. Sometimes people will put sort of a dotted line, a dash line, I guess, to represent that, a dash line here instead of the double bond. I just want to show you something called resonance structure. How it kind of flips around. I'm going to pause the video, update attendance. Isomers. So I'll read, I guess, I have it here instead of the textbook. Sometimes a chemical formula, without a name given, can result in more than one structure. Okay. When a formula has more than one possible structure, we call it isomers. Okay. In medicine and stuff like this, there's isomers and stuff like that. Have you ever heard of levo? That's left, and then what's dextro is the right form. something attached one way, or else it's kind of mirror image-ish kind of thing. We attach different. Sometimes there are structures that are hitched up completely different, but they're equally as valid. Here's an example. I'm going to get you guys to work with carbon and hydrogen. Draw two possible isomers for H3 or C3H4. One will have a triple bond, the other has two double bonds. Now, I'm needing you to figure this out. Each carbon can bond 4 times. It must bond 4 times. Each hydrogen once. So the way I suggest this, because there's no true central atom, hydrogens are always end of their line on their once. So get you started. And you're going to do, I'm telling you there's 2 possible isomers. So maybe start one up like this. Carbon, carbon, carbon. The other one maybe start up like here. Carbon, carbon, carbon. I'm only doing 2 parts. When I do this, I'm giving you a hint. One's going to involve a triple bond carbon. One's going to involve 2 double bonds. You guys fill in those and then attach hydrogen as needed. I'm going to give you some time and pause the video. So in the video, pause and try these out and compare answers. Okay? Okay. Coach me. Okay, what do you do first? Oh, child, adult, okay. No, you're not. Okay. Being a baby. Oh, yeah, that's your point. Okay. I said one has a triple bond. I might as well do it with the first one. So left to right. Let's hitch up the carbons, left to right. I'm just taking a scan here and see. Oh, yeah, good. So I think of carbons hitched up first, then I add the oxygen. See what's happening. Triple bond. Okay. Then this one has to be hitched up with a single bond. When I look at this, then I think this middle carbon has 1, 2, 3, 4 bonds, right? It's done. You can't do anything else. The carbon on the left has 3 bonds. It can bond one more time. That'll be a hydrogen. I will do that. The carbon on the right has a single bond. Get out the model kit. Hope you I does stuff. Somebody might say that, well, hey, is this a different structure? I'm going to do. That's it. Well, I'm going to try it again. Don't draw it. I'm just redrawing the same thing in my head. Anyways, I think left to right always. This is the mirror image. Is it different though? Why not? Ah, yeah. Patches and shoulders. Exactly what you got. If this, the C's will be upside down, but that doesn't represent the other. If I just flip this around, this is the same, right? It's just upside down. And what you can't see on the video is this triple bond. I flip the model, and it is the same, right? I don't have to reattach it. So that's considered the same. You could have drawn it that way or that. Plus, you could have drawn it up and down like this model is right now. Now, the second one. I said 2 double bonds. Let's just go. It's 2 double bonds. Okay. On the left, I have 1, 2 bonds to the carbon. So I've got 2 more left. I'm going to space them out, but I don't care if you go like this. This. I'm going to just start this, but don't erase what you have. I want you to do Okay, the middle one has 4 bonds to it, so it can't do a diamond. Right? So like the middle one or the other. This is it. And I don't even think anyone would say upside down instead of face. Those are isomers. And it's important. We have to have, and we're going to get a naming system. I can't just say C3H4 and know exactly which molecule it is, right? We're going to work our way up to that. We will get a naming system. We can name each one. Over and out. I'm going to stop this video